Thank you very much. So, welcome everyone, and a big congratulations for getting through to the end of the day. I don't know if anyone else is tired, but in a happy way I'm tired because it's been great to chat to you all today. We've got half an hour to get through about 40 minutes of content, and I also want to give you a demo, so we'd better jump in. Research computing is an interesting topic. I get asked what is research computing all the time. People say, oh, you're the HPC guy, or oh, you do big data, or no, you must be the machine learning person. And what I would say is research computing is all of those things and more. Research computing is actually a collection of tools, a collection of very powerful tools. And it's important that we have flexible tools at our fingertips to fit into the way that we work, because one tool is not enough. As researchers, we are working in workflows. We typically have a number of steps that we follow, and if we're dealing with data, I've kind of shown a canonical workflow at the top here, which is pretty representative of what a lot of data scientists or researchers or in different domains do every day. And so typically we are collecting data at some point. This might be from traditional data sources like databases. Perhaps we're doing Earth observation work, and we're maybe collecting data directly from satellites. Or downlinks from satellites. Perhaps we have Internet of Things sensors in the field that we're collecting data from, and so on. You get the idea. But then we're also generating events. We're either generating events in reaction to data streams that are coming through. Perhaps we're putting data into S3 and events are being generated that way. Maybe we're using our software development kits to generate events based on changes that are happening in data streams, or we're capturing real-time feeds of information through a service like Amazon Kinesis. And then we have the concept of workflows, where we're running analysis. And there are two main models we see. The first is batch. Batch workflows are typically not time-sensitive. This is where it's okay for you to wait several hours or maybe several days for a result. We have customers that do very complex analysis in the cloud, and they can sometimes wait several weeks for a result. So the point is that what they typically do is land data into S3 as a storage service. They then spin up tools like HPC clusters, like Hadoop clusters, using AWS batch potentially, to do some kind of analysis that is time-consuming, that is batch-driven, and then they write the results back out to S3. So that's one model that we see. Another model that we see commonly is real-time workflow. So this is where time to a result is much more important. Perhaps we're asking questions of data that we need results in seconds to. Or perhaps we're doing real-time analysis of streaming data. Perhaps we're looking at window analysis, those kinds of things. And so here I've represented common tools that are used by our research community like Spark, Apache Spark. That's trivial to run on EMR, our Elastic MapReduce service, which is a managed Hadoop platform on the cloud. Okay, it's a checkbox when you want to create a Spark cluster to be able to do that kind of work. Or maybe we're using Lambda, a serverless platform to react to events and process data as they come through in a stream, and so on. But then ultimately what we're doing with those results or those answers or those secondary data products is we want to share them, and we want to collaborate, and we also want to be able to make those results available so other people can validate them. And so we may use tools like Jupyter Notebooks, or maybe we're using Zeppelin on top of Hadoop to start doing some kind of interactive analysis of our results. You get the idea. Now, where does HPC fit into this? Where does machine learning fit into this? It is a tool in a workflow. And it's important that you choose the right tools that are flexible enough to be able to be strung together to suit your evolving workflows as a research community. And that's one thing we spend a lot of time thinking about carefully at AWS. So let's talk a little bit about clusters. Clusters in the cloud are an ephemeral tool. Now, what do I mean by that? Well, it's very common for data to come in from sources that we've talked about a little bit already and land that into S3, because S3 is durable. It's very scalable, and it's actually very cost-effective. So it's very common to use that as the sink for your data. And then we can generate an event and spin up a cluster on demand. So we can actually, in a completely automated way, spin up a fully fledged HPC cluster to do high-throughput computing or high-performance computing on that is just ours. No one else is sharing it. And we can have that for as long as we need to. We can connect to that over RDP or remote desktop or VNC or SSH, our usual methods. We can connect to a login node, and then we can pull data into the shared storage environment of that cluster. We can do our processing in a batch-driven fashion, perhaps, on that cluster. We can write the results back out to S3, and then what do we do with the cluster? We can get rid of it. We don't need it. The cloud presents a model where you only need to spin up the resources that you need, and you only need them for the time to do the investigation. And when you couple that with an on-demand model for how you pay for these resources, you start thinking about these tools as just being ephemeral steps in a workflow. It's very different to an on-premise environment where you have a shared infrastructure that lots of different people are using, and you're trying to perhaps get in a queue or trying to change the job specification to run on the cluster faster or only use a part of the cluster, and you're invariably fitting your job to fit the infrastructure. Here, we're able to get the infrastructure quickly and automate that, and the infrastructure gets out of the way so we can do our research. Now, the cloud's also pretty interesting because it gives us a huge ecosystem of tools and compute environments and compute types. So it's very flexible in that sense. And here I've shown what we typically call our instance families. We have general purpose compute, we have compute optimized, storage optimized, you get the picture. We even have more modern instances that give you accelerator options, give you GPU for general purpose GPU compute using CUDA or OpenCL. And we also have, more recently, an instance type that gives you FPGAs on the server. And so we're seeing our researchers, in some cases, move towards these accelerator options to speed up their processing. And so what this means in the cloud on AWS is that you can build fit-for-purpose clusters. So if I'm going to do deep learning work, and I know that I can accelerate the training of my deep learning models with GPUs, then I can spin up a cluster based on GPUs for the period of time that I'm doing my training. Maybe that's a few hours, maybe that's a few days, maybe that's a few weeks. But then when I'm done, I shut it down. Or maybe I know that my computationally intensive workload, maybe I'm doing weather modeling, and I know that I can take advantage of the latest Intel architecture based on Skylake. Okay, maybe there are extensions to the architecture that let me go faster for my processing. And we can use the C5 instance family, which is an instance family we've pre-announced that will support Skylake, the new Intel Xeon architecture. And so you can start thinking carefully about your workloads. Most of you understand what workloads require what infrastructure, and you can build fit-for-purpose clusters for that. Okay, and this arrives at better efficiencies than trying to share a shared environment, even if that shared environment is heterogeneous. Okay, this is your tool, this is your cluster, and you can use it how you see fit. Within, okay, I've just skipped over something here. Oh, okay. Within families, we have different types of instances. You're probably familiar with this. This is the R4 family that's memory optimized. This lets us choose small instances with just a couple of CPUs, and at the top end gives us 0.5 terabyte of RAM per node. What you'll also notice there, though, is network I/O performance scales with instance type as they get larger. And so at the top end, we're giving you 25 gigabits per second performance now, I believe. It was 20, and now we've released 25 gigabits performance. And that's Ethernet, and that's excellent throughput for each node. So when you're doing high throughput computing in a cluster, you can get that kind of interconnectivity as well. I'm going backwards, sorry guys. A little bit about our accelerator options. So the P2 instance family gives you K80 GPUs. They're NVIDIA K80 GPUs. And these are commonly used for modeling, financial simulation, deep learning, anything that you can offload to do general purpose kind of compute on a GPU. And we give you up to 16 of these actually on a single instance. And we give you very good interconnects between those GPUs so that you can start doing multi-GPU work. I don't know about you, but I only have one GPU in my laptop, and even if I go and buy a workstation, it's hard to get 16 of these. They're industrial strength GPUs, and we're also going to be supporting Volta when that's released later in the year. The FPGA instance type, the F1 instance type, gives you Xilinx FPGAs. Similar idea, except you're writing your own using a sort of a high description language, a hardware description language. You're writing your own code that you're deploying to the FPGA. and we give you a software development kit and a hardware development kit to be able to do that easily. And we also take care of the I/O mapping so that you're just focusing on the core logic that you deploy to an FPGA. We have partners that are using that instance type, actually. Edico is one of our partners that has released a FPGA-enabled product into our marketplace. And this is for genomic processing. So they've optimized some of the pipelines that they run typically for analysis of genomes, and they've made that entire tool set available in the marketplace, accelerated with FPGAs. Who's heard of elasticity? We've all heard this term elasticity. We've talked about it in terms of web environments and other environments, API designs and what have you. It makes sense in scientific computing as well. So we can scale the clusters that we use, right? Here I've got a cluster that has, a head node, some storage, some compute nodes, and it's doing a unit of work, right? It's doing a unit of work for a unit of cost. But if I want to address a larger data set, I can scale in terms of space. I can add more nodes. That might let me address more data. It might let me do more complex analysis. And I'm doing n units of work for n units of cost. But what if I don't have any work to do? What's the largest cluster size? It's about 0, or it's a login node with some shared storage. I could even tear the cluster down like I showed earlier. But maybe I want that cluster around with shared storage available with data sets on it, and I scale the compute nodes down altogether. So that's maybe to go bigger. But I've got another dimension I can scale in terms of time, right? So this is like a time-traveling cluster. So what I can do is I can say, look, for that cluster, I'm going to do some work over a period of time. And in the case where I'm adding more nodes, well, maybe I don't address more data or do more sophisticated processing. Maybe I just process much, much faster. I get to my result faster. And if my software scales appropriately, that's another sort of dial that I can turn. And again, with an empty cluster, there's no argument about what work we're doing in what time. But you get the idea. So you can think about how you optimize for a problem. You either go bigger and more complex, or you go faster. And elasticity lets you do that. No talk about research computing would be complete without talking about data. And specifically about how data is consumed. So, I've been a little cheeky here, and I've taken something that a phrase that we bandy about. Has anyone heard the phrase, data has gravity? Everyone has. Hopefully everybody has. So I've taken the Newtonian model of gravity here, and I've sort of mangled it and turned it into a discussion about data. So it's kind of curious. But what I'm saying here is that there are some characteristics that we care about when we're thinking about data in the context of research. They are, how much data do I have? How much data do I have in relation to other data sets? Because often I'm mashing data sets together, or I'm doing correlation, or I'm looking at variance, or I'm doing work where I want to compare against other data sets. And then how accessible is that data? So maybe it's not inversely proportional like this, but if I have to wait 2 weeks to go and get a data set and give somebody a hard disk and they go and retrieve it out of a basement and give it to me, and if my iteration cycle is something like a week or 2, then maybe the pragmatic value of that data is reduced. So we have to think carefully about how far away our data is, how accessible it is, and how large it is. Now, in the cloud, in AWS, it's generally true that almost everybody consumes S3 at some point. This is a pattern we encourage our research community to follow. We're generating data, we land it into S3 as quickly as possible, and then we consume it out of S3. So in the case of EMR, our Hadoop service, we have a native integration with S3 that replaces HDFS with S3. It scales, its throughput is fantastic, and it integrates nicely. And then we have the ecosystem of Hadoop tools on top of that, like Spark and Tez and Pig and what have you, at our fingertips. But even in the HPC world, where we want POSIX compliant file systems, and we want POSIX APIs, we can do something similar. We can still land data in S3, and we can then pre-stage the data and move that into maybe a clustered file system. Intel Lustre is in the AWS marketplace, BGFS. EFS is our managed NFS v4 service that does a similar thing, all giving you commonly used POSIX compliant type interfaces that we can then use from clusters, maybe on AWS out of EC2 and so on. We keep storage simple though. A lot of you have told me that you can't natively integrate with S3 because it's an object storage service. You need POSIX. Well, in that case, let's take something like a BGFS scale-out clustered file system architecture. And let's do something where we treat that as a long-lived POSIX cache. So we keep our data in S3. We have a VPC here in a subnet with a S3 endpoint that lets us get it data quickly and securely. We have a management host in that subnet that manages the scale-out clustered file system. And then in BGFS, there are two types of servers. There's a metadata service that does name lookup. When I ask for a file, it knows which storage service to go and retrieve it from, and they scale out and are redundant. And then I have storage servers as well with block devices attached, maybe SSD-backed storage, so it's fast, and they also scale out. Now what I can do is I can lifecycle data as part of a research project out of S3 into a clustered file system like this. I can access it from clusters that want POSIX, from services that want POSIX compliant interfaces. I can do my processing at speed, at scale, quickly, reading and writing data to that shared file system, and then when I'm done, I can move the data back out into S3, and I can shut down the file system. And we have automated tools that will build clustered file systems like this for you, so there's a new model there. I'll quickly talk about some HPC and some high throughput tools. On the left, we have CFN Cluster and Alces Flight. CFN Cluster is one of the tools we've created. It's open source, it's in GitHub. There's a Python command line wrapper for it to make it easy to use. And it lets you spin up your own high performance computing cluster, lets you choose the scheduler that you want, the number of nodes, and it auto scales for you as well. So it does all the plumbing and all the automation of what is a fairly sophisticated piece of kit or tool for you, and it takes about 10 or 15 minutes to get that cluster. Alces Flight is one of our partner products in the marketplace. It's a little similar to CFN Cluster, but what makes it different is it's much easier to use, and it's also bundles up over 1,000 commonly used scientific computing applications, and I'll demo that in a couple of minutes. Batch is really focused on more of that batch processing model. And it gives you the ability to define your software in Docker containers, deploy that to Batch as a service. Batch manages the distribution of work across that using a scheduler and gives you concept of queues, and it can use Spot Fleet under the hood to reduce cost by using Spot. And Amazon EMR is our managed Hadoop service, and you get Spark and all the ecosystem tools on top of that. So a little bit on Flight, because I'm about to demo it. Flight's great because it gives you lots and lots of applications. So it's one thing to get a cluster, but it's one thing to immediately be able to do something interesting on that cluster with software. And so that's the difference here. It also supports Slurm as the default scheduler. It supports Docker. It also supports Singularity, which is interesting for some of our HPC customers. And the really cool thing is it's available via Marketplace. So it's literally a couple of clicks to deploy one of these things. So what I want to do is kind of take you to a demo in a second, and I want to pose the question, what if it was as easy as pushing a button to get an HPC cluster? We could call it push button HPC, perhaps. And any of you that have been talking to us for a little while have probably seen one of these things. It's an IoT button, right? I don't know if any of you have programmed one of these. It's really easy. But what it effectively lets you do is hook up a Lambda function to the push of a button. It's about as complex as that, and that Lambda function can do anything. So why not make that Lambda function call CloudFormation to build an HPC cluster based on Alces Flight? So what I'm going to do here is I'm actually going to push this button. It's blinking white, and it's gone green, which means it can connect to the Wi-Fi, so we've passed that hurdle. But then hopefully something interesting is happening on the other side of that. So if we can flick to the laptop, so what I have here is CloudFormation, and I've just refreshed it, and what it's showing us is that we have a brand new CloudFormation stack that's just being created. Now, this is no simple stack, okay? This isn't just spinning up a load balancer and a couple of web servers. What this thing is actually going to go and do is create an entire clustered environment for me, but that's not enough. It's going to also go and make sure that I have over 1,000 scientific computing applications at my fingertips, and then I can do whatever I want with this cluster. I can do things that my existing cluster admin would never let me do. I can log into the head node, and I can install software. I can run GUI applications. I could do all sorts of crazy things. Because maybe I want to do that. Maybe I'm testing something that does sound crazy. Maybe I do want to try an experiment that no one else has tried before. So using a model like this, I'm able to have complete control of that. So it takes about 5 to 10 minutes to go off and create a cluster. And so, of course, what I did earlier was prepare one. And so I'm going to actually log on to it and show you what that looks like. So I'm already logged on. But what I'm doing here is SSHing to the head node. I get some nice ASCII art, of course, because we're connecting to an HPC cluster. And I get a lot of sort of help text here that sort of gives me some guidance on what I might want to do initially. And one of the things that's interesting is to look at something called gridware. Gridware is this location or a repository that gives me access to a ton of tools. A lot of these tools, when I show researchers this interface, a lot of these tools are familiar. There are people that will say, yeah, I use Blast or Beast or Bowtie, or I'm using OpenFOAM to do computational fluid dynamics, or I'm using Bioconductor or BioPearl. We support, well, Alces supports, through this interface, lots of different research domains. And it's as simple as, say, choosing one of these things. Let's say we want to try and install Bioconductor. It's as simple as saying Alces, gridware, install Bioconductor. And what it'll do is it'll say, look, there's some dependencies. Do you want to go in and install all of those? And I say yes, and then it'll work out all the dependency mapping, and it'll go and download those from a precompiled repository of modules, and it will install that across my cluster for me in a sane and complete way. And it will use the module system to enable me to turn these on and off, and I can even have different versions of the same packages installed. I can extend this with my own repositories and my own software, and it's really as easy as that when I want to go and start doing some work. I should have probably tested this one before I tried it because it looks like it's going to take a while. Okay, it's worked. And so then I can do module avail. What have I got available? And lo and behold, I've got Bioconductor. I've now got R installed and Bowtie and a whole bunch of other things that are dependencies for that to work. And then I can just turn those modules on and use that software. But that's actually not what I wanted to show you today. What I wanted to show you, I'm sorry, I'll just change to slideshow from here briefly. What I wanted to show you in the last couple of minutes was how to work with something that one of our partners has built in Australia, which is to sort of take advantage of drone imagery and do some processing of that in a cluster. And so the cluster that we've spun up lets us use something called OpenDroneMap. It's all installed for us. It's been installed in a Docker container, and in fact, it's already running across my cluster in Docker with all the libraries and dependencies that I need. And what it does is it lets us, OpenDroneMap, for those of you that aren't familiar, lets us take lots of different disparate images of an area, build a mosaic out of those, and auto-rectify them, and then it also generates a point cloud as well, based off the imagery that we've supplied to it. And so what we can do with Alces Flight is we can send one job to one node, send another job to another node, and we can scale in a kind of a pleasing, embarrassingly parallel fashion across multiple nodes. So what we'll do is we'll get back to our cluster and we'll actually look at it. sinfo, oops, I'll just go back to, get out of presentation mode. So if my screen wakes up, what I'll do is I'll type sinfo, and that queries the Slurm scheduler on the cluster and says, how many nodes do I have? Well, I have 4 R48 extra larges, and that's giving me some decent capacity. And I can also see what's running on the cluster by typing sq, and there's nothing running at the moment. What I've done is I've taken the liberty of kind of pulling some data onto this cluster already, and there are already a set of data sets that I can work with. These are just part of the project. So what I can do is do bash odm, actually, yeah, I'll just run this. Bash odm runner, and I can just pick one of these projects. And you can see that a job has been submitted to the cluster. Now, if I look at sq, you can see that, I'll just move that up on the screen a bit. You can see that I have a running job. The status is running. It's using the Alces username, and we know exactly what node it's running on. And if I kick off a bunch of these jobs, then the scheduler will just go and send those across different node members. Okay? In fact, if we start queuing up the cluster with more and more work, then the cluster will actually auto-scale, and we'll start adding more of these big memory nodes, and subsequent jobs will just get farmed out to those nodes. Now, this actually takes about 3 hours to run. It's computationally intensive. So what I've done is I've prepared something earlier. And this is the mosaic that's auto-rectified that it generates for us. So I don't know if you can see on the screen. I'll just make that window a little larger. So you can see something that looks like a bunch of drone images that have been joined together. And it's done some calculations to work out how to do that properly, and in a sense that's keeps the integrity of the geospatial data as well. The other cool thing that it's done for us is it's generated a point cloud. So this point cloud looks a little bit like the mosaic that we just saw. But what I can do with it is I can actually zoom in. So I can move around. I can look at this a similar view of what we had before. I can maybe, say, tilt it around, and I can look at the foliage, and I can look at maybe the elevation that it's determined based off the algorithms that it's using. It's worked out foliage height. I can do land mass calculations this way, or biomass. I can look for land subsidence. I can start generating these point clouds over time, and then look at differences in sort of contours and things like that. So this is actually a real-world example of how you can use a cluster to speed up the processing that you're doing. Now, if we can go back to the presentation quickly. I'll have to finish fairly quickly. How much did this cost? Well, we had a login node. We had 4 of these large compute nodes. I had a terabyte of SSD storage. I had a little bit of egress cost for data moving around. It cost me about $5, $6. That's the price of a cup of coffee in Sydney, right? So for 3 hours or 3.5 hours of processing, I am able to do some interesting work. And remember, I'm able to put this into a workflow where this tool is created automatically for me as part of maybe an event-driven workflow where data lands in a bucket. I spin up a cluster, I do this work, and I shut it down and persist the data elsewhere. I don't expect many of you will go off and start launching clusters from IoT buttons. I will when I show the demo to future customers because it's kind of a cool, neat trick. But in the real world, you'll actually be integrating this into workflows. Now, quickly, evolving the paradigm, some ideas about the future where we see research pushing the compute paradigm. I'm not going to talk about physical or virtualization. Containerization is interesting, and I guess it's been around for a long time too, and Docker has certainly made it a lot easier to use. But I think where things get much more interesting is where we remove the server from the picture altogether. And anybody that attended the keynote this morning heard the story from the Genome Institute of Singapore, who are starting to investigate work like this. And the benefit of thinking about serverless is we're actually not thinking about servers. We're not thinking about operating systems. We're thinking in the paradigm of software. We're writing code to solve a research problem, and Lambda, in the case of AWS, is going to run that code for us at scale. And that frees us up to focus on our research problem. And as researchers, that's really what we want to be doing. We don't really want to be building clusters or thinking about operating systems or patching or lifecycle. You get the idea. Actually, Werner Vogels, our CTO, has a great phrase: no server is easier to manage than no server. And HPC on Lambda, is it possible? Yeah, it actually is. We heard from the Genome Institute of Singapore this morning in the keynote. In Australia, we have the CSIRO eHealth group working on similar problems. They've implemented a completely serverless pipeline using Lambda. And come and talk to me if you want to know more about that. It's a very nice cloud-native way to do what is traditionally a big HPC search problem. And UC Berkeley, Rise Lab out of UC Berkeley, have built something called Pyren, which takes your existing Python code and farms that out across many workers running on Lambda. And they've done some benchmarking, and they achieve up to 40 teraflops peak compute, which is actually a very respectable compute number. And they've benchmarked S3, and they're seeing performance around 80 gigabytes per second out of S3. That's getting close to a terabit throughput. That's serious throughput. I said S3 scales, it really does. So we do have customers doing this. It is real. It's not going to solve all your problems, but there is a subset or a class of problems where Lambda can make some of your compute challenges as a researcher tractable and lower the cost at the same time. So 2 things before you go. I'd love you to go and register for our cloud program. We have the Research Cloud program. It lets you download a researcher's handbook. This handbook is written in your language. As a researcher, you will understand what we're talking about. And then I want you to go and try launching your own personal cluster, because I think you'll be pleased at how easy it is and what you can get done with it. We have lots more information. I'm way over time, but please come and speak to me afterwards, and I'd love to hear about what you're doing in research and how we might help. And thank you so much for your attention today. I hope it's been good. Thanks.